Hello, my dear students. Welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel and press the bell icon to get the regular updates of the upcoming lectures. In the previous lecture, we have done that larger electronegativity difference between the combining elements will give rise to the higher polarity in a chemical bond. That higher polarity is measured by dipole moment, and it's our topic for today's lecture. So, dipole moment is the property of the molecule by virtue of which we evaluate the extent of polarity in that molecule. Let me take an example. I'm taking the example of hydrogen chloride. That's hydrogen having one electron, and that's chlorine, and that's the electron of chlorine. And these two electrons will form a single bond between the hydrogen and the chlorine. So, in the previous lecture, we have done about the values of electronegativities. The value of electronegativity of chlorine is 3.0 and that of hydrogen is 2.1. So, in this case, electronegativity difference comes out to be 3.0 minus 2.1. It comes out to be 0.9. It signifies that I'm writing it signifies that bond between hydrogen and chlorine will be polar. So, in this case, the chlorine is having higher electronegativity. So, what will happen? Chlorine will attract the shared pair of electron towards itself. So, this bond will look like hydrogen, and that's the chlorine, and the both electrons are more closer towards the chlorine than the hydrogen, due to which what's going to happen? Due to which chlorine will acquire a delta negative charge and hydrogen will acquire a delta positive charge. So, value of this delta, I'm ignoring the signs. The value of this delta will be directly proportional to the electronegativity difference of the combining elements. What next? Now, after that, I'm taking the distance between hydrogen and chlorine. You can call it to be bond length. The distance between hydrogen and chlorine to be small l. So that will be called as bond length also. Now, dipole moment. Now let's talk about dipole moment. The dipole moment has a symbol mu, and this mu will be equal to the amount of charge separated. I'm ignoring the signs, I'm just saying amount of charge separated into bond length, where obviously this delta is magnitude of charge separated. I'm writing this delta is magnitude of charge separated. Hydrogen and chlorine will have equal values of delta but with opposite signs. And what about L? L is the bond length, or you can also say distance between two oppositely charged poles. So, what is dipole moment? So, dipole moment is the product of magnitude of charge separated and the bond length. So how can we define dipole moment more precisely? We can say that dipole moment is defined as the product is defined as the product means multiplication in this case, not the product of the reaction. I'm talking about the mathematically product is multiplication. Dipole moment is defined as the product of distance separating distance separating the charges and the magnitude of charge separated, and the magnitude of charge separated. So that's the exact definition of dipole moment. So dipole moment can be defined as the product of distance separating the two charges and the magnitude of charge separated. So what next? Let me rewrite this formula. So I'm writing dipole moment will be equal to the magnitude of the charge separated into bond length. Now, let's talk about the units of the dipole moment. I'm taking the unit of length to be centimeter over here. The unit of magnitude of charge to be electrostatic units. So that's a CGS unit of charge. That's ESU. ESU stands for electrostatic unit. That means the unit of dipole moment will come out to be electrostatic unit centimeter. But the SI unit of dipole moment is dBi. I'm writing SI unit of dipole moment is dBi, DEBYE. Now, there's a conversion factor of dBi and the electrostatic unit centimeter, and that's 1 dBi will be equal to the 10 raised to the power minus 18 electrostatic unit centimeters. So now, that's all about the dipole moment. Now let's compare the dipole moment of hydrides of group number 17 according to this formula. So I'm writing hydrides of group number 17. Hydrides of group number 17 of periodic table. And the hydrides will be hydrogen fluoride, hydrogen chloride, hydrogen bromide, and the hydrogen iodide. Now, as we move down the group, what's gonna happen? As we move down the group, the electronegativity will decrease. The electronegativity will decrease. Thereby, what's gonna happen? Thereby, charge separation in a bond will decrease down the group. Will decrease down the group. So what's gonna happen? In this case, magnitude of delta will decrease. What's delta? Obviously, that's the magnitude of charge. So in this case, as we move down the group, the electronegativity will decrease. Thereby, charge separation in a bond will decrease, due to which the magnitude of charge, that is delta, will decrease. On the other hand, as we move down the group, what's gonna happen? Size of the element will increase. Size of the element will increase, due to which the bond length L will increase down the group. Now, in this case, delta, the magnitude of charge, is decreasing down the group and the bond length is increasing down the group. But we have the formula of dipole moment to be delta into bond length. So in this case, delta will be the deciding factor. The magnitude of delta will dominate over the bond length. So dipole moment will depend on the magnitude of charge, not on the bond length. So I'm writing, in this case, magnitude of delta will dominate bond length. So the dipole moment, so in this case, that is the hydrides of group number 17, the dipole moment will depend only on the magnitude of charge, which is decreasing down the group. So the dipole moment will decrease down the group, will decrease down the group, because in this case the magnitude of delta is the deciding factor, not the bond length. So the dipole moment will decrease down the group as the magnitude of charge, that is delta, will decrease down the group due to the decreasing electronegativity down the group. Now, what next? Let's discuss more about the dipole moment, and it's now a very important point which I'm going to discussing. Up to right now, I have just taken the diatomic molecules. Like in case of HF, we are having one H and the one fluorine. So that's the diatomic molecule. So let's talk about the directions. The dipole moment is a vector property. What are vectors? The vectors are those properties that depends upon the directions. So let me rewrite the HCl again. So that's our hydrogen forming single bond with chlorine. Chlorine will acquire a delta negative charge and H will acquire a delta positive charge. So in this case, the direction of dipole moment will be towards the negative pole, and a positive charge at the end of the arrow at the side of positive pole. So that's called dipole. The arrow shown in yellow color is called dipole, and it depends on and it's a vector quantity which depends upon the direction. So this arrow, this single-headed arrow, is also called dipole. The word dipole is given to this arrow. So I'm writing, dipole moment is a vector quantity. Dipole moment is a vector quantity. Comma. That is, it depends on directions. That it's depends on directions. So, up to this point, we have just studied about the diatomic molecules. But from the triatomic molecules, the resultant vector of all polar bonds of the molecule will decide the extent of polarity of the whole molecule. Uh, that means in some cases, let's take an example of carbon dioxide. In carbon dioxide, we are having two polar bonds. But in the net result, we get the carbon dioxide molecule to be non-polar. Even the presence of two polar bonds is there. So, why so? Because we have to take the resultant vector of all the dipoles or all the polar bonds in a molecule, which we will discuss in the next lecture. From the next lecture, we will be discussing about the triatomic, tetraatomic, pentatomic molecules and their resultant vectors to talk about the extent of polarity in whole molecule. So, I am writing from triatomic molecules. From triatomic molecules like CO2 or SO2, comma, the resultant vector of all the dipoles, or we can say all the polar bonds, will decide the extent of polarity, will decide the extent of polarity in a molecule. Let me give you an example. Carbon dioxide. The carbon dioxide molecule is having two polar bonds. Let me take another example, sulfur dioxide. This sulfur dioxide is also having two polar bonds. But on the whole, carbon dioxide molecule is non-polar. But SO2 molecule is polar. Because in case of carbon dioxide, the resultant vector of all the polar bonds or all the dipoles come out to be 0, whereas in case of sulfur dioxide we got the resultant vector greater than 0. So sulfur dioxide is a polar, whereas carbon dioxide is non-polar. So we will be discussing about the resultant vectors of different types of geometries and the structures that we have done in the hybridization to explain the net polarity of whole molecule rather than the single bond, because till now we have done the diatomic molecules. In diatomic molecules we are just having one bond, or we can say only one dipole, so obviously it is a polar. But from triatomic molecules we have to take the resultant vectors. So that's all for today. I hope you all understood the topic dipole moment. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.